Hello, in this lecture, we are going to discuss something about expectation values. So what do we mean when I say expectation value? So loosely, I can say that these are nothing but these are mean values or average values. But the only thing is that these mean values are or average values are nothing but these are then why the term expectation value? Expectation value in some sense are long-term averaged or long-term mean values. So basically, when we want to calculate expectation value, an experiment is repeated time and time again. So, and then the mean value that turns out is called as the expectation value. Then the mean value that turns out is called as the expectation value. So more formally, I should write that expectation value is also referred to as the long-term average values or long-term average mean. You can take it as mu. Okay, but long-term average means what? It means that over a long term, that is by repeating experiments. By repeating experiment over and over again. One can expect this average value. One can expect this average value. Okay, so the only difference is this. Okay, so let me take an example and let me write for you how to find this expectation value. It is quite easy for you to find this expectation value. Expectation value for a discrete random variable capital X, as I have written, is nothing but it is equals to summation X times Px. Okay, so what is expectation value of a discrete random variable X? So expectation value of a discrete random variable X is nothing but X multiplied with its corresponding probability at X, or you can say that X multiplied with the probability distribution function. Let's say if there is a probability distribution function assigned, then you can write it as Px. And if you know the probability Px for every X, then it is X into probability. Okay, so this is how you actually find. So basically, this is the definition for mean only. The only difference is that whenever I'm saying expectation value, I would mean long-term average values. That is, whatever probability I'm getting here, it is an outcome of many experiments together. Okay, so like many experiments time and again have repeated, then I get some probability for a particular X, or I get a probability distribution function, then I find something called as expectation value. So for a discrete random variable X, if Px is the value of the probability distribution at X, so let us say that this Px is what? It is the value of the probability distribution at X. At X. And this is simply a random variable. So basically, X into Px would give you the uh, expectation value of the discrete random variable. This is point number one. The same definition can be extended to the continuous case. So instead, if I have capital X, that this particular thing is, let's say, a continuous random variable. It is a continuous random variable. Then the expectation value is simply given by an integration now from minus infinity to plus infinity x into px dx. Now here this x is the various, you can say, values for the continuous random variable. This is the value of the probability distribution function. Okay, so this is the value of the probability distribution function, PDF. Okay, so this is one thing. Okay, now if at all it happens that the probability in totality should come as 1. So basically, the necessity is that the total probability should come as 1, right? So total probability of any event, total in totality should come as 1. If it is not coming as 1, then you can do this thing. Then one can do this thing, that is from minus infinity to plus infinity, x px is fine, and divided by minus infinity to plus infinity px dx. So if the total probability, this particular integration is not coming as 1, then you can use this definition to find the expectation value of a continuous random variable, and similar thing that you can do it in your discrete case as well. So let us take an example. Let us consider that a physics scholars football team, so let us say physics football team, because physics people have less time. So let us consider that, let us say that a physics football team plays football in a week. Okay. And let us say that they play for 0 days with a probability of 0.2. They play for 1 day in a week with probability of 0.5. And they play twice a week with a probability of 0.3. And we are interested to find the expectation values of number of days per week the physics football team plays. Okay, so we want to find the expectation value of number of days per week the football team plays football in a week. Okay, so how do I get it? I'll get it simply x into px. Here probability is given to me for the corresponding can say random variable. So here random variable is number of days. So number of days, if it is 0, then the probability is 0.2. So I'll write px here. So it is 0.2. If the number of days is 1, then it is 0.5. And if the number of days per week is 2, then it is 0.3. And you can calculate the sum is 1. So summation px is 1, so no need to divide anything. So you'll get simply summation 0 into 0.2. Sorry, not summation. 0 into 0.2 plus 1 into 0.5 plus 2 into 0.3. So answer would be, I think, 1.1. So on an average, or you can say the expectation value. Okay, so the football team is expected to play 1.1 days per week. So the football team is expected to play 1.1 days per week. Okay, now let us consider some continuous examples. Okay, so consider that a probability function is given to us for a random variable x, and it is equals to x exponential of minus of x upon lambda. And here x is positive. We want to find what is the expectation value of x. So expectation value of x would be simply 0 to infinity x into fx. So fx is already this, so this will be x square exponential of minus of x upon lambda dx. And here also from 0 to infinity x exponential of minus x upon lambda dx, because I don't know whether the total probability is 1 or not. So I have divided it by that, so that I would get a constant which when multiplied with this would give me 1. The total probability is 1. So if you remember from Laplace transform, e to the power minus st t to the power n dt is simply n factorial upon s raised to power n plus 1. So this integration turns out to be this if n is natural. So from here, it is quite clear this would be 2 factorial divided by 1 factorial. And okay, in order to make it in this format, what you can do, I can take, so let us consider here that let's say x is equal to lambda t, so that things would be easy for you. So if x is equal to lambda t, then this particular thing would be slightly the same, I think, but here you will get a lambda square, and this would be t square e to the power minus t, sorry, dt. So this would be lambda cube, and divided by lambda square 0 to infinity, and here you will get simply lambda t, and again a lambda dt would come here. So it is lambda square, so it would be t exponential of minus t dt. So I hope it is clear. Now using this formula, you know this s is 1 here. So you will get, I think, here lambda cube would also come, and here lambda square would come. So eventually, the expectation value of x is simply 2 lambda. What do you think this lambda would be? Just pay attention. So basically, if I want to find what is that particular value for which my probability density function peaks. So let me give you an example. So let's say this is exponential minus x upon lambda. Here lambda is positive. If I have not mentioned it, please understand this is positive. As x tends to 0, this is 1. As x tends to infinity, it is going towards 0. And as x tends to, so sorry about it. So as x tends to minus infinity, so but minus infinity is not there, so it will start from here and it is a continuously decreasing function. Okay, now I understand it is peaking at x equal to 0, so it is giving me the peak at x equal to, okay, so this is not peak. Okay, so this is giving me peak at x equal to 0, fine. But what about x into exponential of minus x upon lambda? So this is our function. So sorry about it. This is our function f of x. And we want to know where does this, where, what, for what value does this probability distribution fx has a maximum? We want to know that. We want to know that. So as you know, if I want to draw this function as x tends to infinity, f of x will go towards 0. Why? Because always remember x upon exponential of x upon lambda. If I take x tending to infinity, this will be equal to 0. Whether you apply L'Hopital rule or what you can do is, you can understand that the rate of growth of x would be very, very smaller than the rate of growth of exponential. So exponentially, if I'm taking the values in the denominator, I know that if I'm taking some very large values, then this exponential rise would be too much than this linear rise. So basically, x upon exponential x upon lambda would obviously go towards 0. And what would be the value at x equal to 0? It would be simply 0. Okay, now if you differentiate, I think if I differentiate this value, I'll get the maximum or minimum. Let me see what it is. So I'll get simply exponential minus x upon lambda minus x upon lambda exponential minus x upon lambda. Let us see if I equate it to 0, I'll get x is equal to simply lambda. If I again differentiate it, so what I'll get minus 1 upon lambda exponential of minus x upon lambda. Again, I'll get from here, so it will be minus 2 upon lambda. And then plus x upon lambda square exponential of minus x upon lambda. If I calculate it at x equals to lambda, certainly I'm going to get a negative sign. You can see lambda upon lambda square would give me 1 upon lambda, and here already I have a minus 2 upon lambda. Certainly I will get a negative sign. So x is equal to lambda. X is equal to lambda is that point where my probability function is maximum. This value is referred to as the most probable value. this value is referred to as the most probable value. So expectation value that I got was simply 2 times lambda. So it is simply 2 times the most probable value. Most probable value is that value where your probability density function is maximum, or simply probability density is maximum. So basically, let me write it as x cap. So 2 times x cap is equal to simply expectation value of x. So if I want to write the ratio would be simply 2. I hope it is clear. Now let us take one more example. Instead of x, if I am supplied with other function, okay, if instead of x, the steps would remain the same. The steps would remain the same. So let us consider one more example. Let us consider that let us consider x to be a continuous random variable, a continuous random variable which is uniformly distributed over the real line from x equal to 0 to x equal to infinity, according to the probability distribution function f of x given by e raised to power minus 4x. We want to find the expectation value of cos 4x. The expectation value of cos 4x. Okay, so how to go about it? Simple, it is quite simple. See, if I want to find the expectation value of x, I had multiplied x by f of x. Now, if I want to find the expectation value of cos of 4x, then I have to multiply cos of 4x with the corresponding probability distribution function. Okay, so I want to find the expectation value of cos of 4x. It is equals to integration from 0 to infinity e to the power minus 4x times cos 4x dx divided by integration from 0 to infinity e to the power minus 4x dx. This is in order to understand the uh, total probability in the entire range should be equal to 1. So basically, I should multiply some constant a and find the normalization constant. If I don't want to do that, I'll do this. Now, what I can do from complex, at least you know this thing, that this particular fellow, that is cos 4x, can be written as e to the power of iota 4x plus e to the power minus iota 4x divided by 2 upon this integral. So integration from 0 to infinity e to the power minus 4x dx. So what I'll get from here, I will simply get expectation value of cos 4x is simply equals to exponential iota 4 minus 4x divided by plus exponential minus iota 4 plus 4x divided by nothing divided by, so it will be negative. So I'll directly write negative here. This will be iota 4 plus 4. Okay, and half would come, and from here I know it's okay. I'll write it once, otherwise there would be some mistake. So half will come here from 0 x equal to 0 x equal to infinity, and this whole divided by e to the power minus 4x upon minus 4. So this is e to the power minus 4x divided by minus of 4 from 0 to infinity. Okay, now just think about this. So expectation value of cos 4x is simply equal to, see, if I place infinity, just think about it. Just think about it. So e की power iota 4x is a bounded function. This is a bounded function anyway, because after all, it is a linear combination of some cos 4x plus iota sin 4x. So this is bounded. However, what is multiplied to it, e की power minus 4x, this is not bounded. In fact, it goes towards infinity as x tends to minus infinity. However, we are not evaluating it from minus infinity to plus infinity. We are evaluating it from x equal to 0 to infinity. So this is a bounded function. You will get some finite value here. And as x tends to infinity, here, this particular value would come as 0. So 0 into any finite value would be simply 0. So again, I'm reiterating. See, e power iota 4x, this is a bounded function. So even as x tends to infinity, this will remain bounded. So you will get some finite values here. And e की power minus 4x, as x tends to infinity, this would go to 0. So at infinity, I'm going to get this as 0. At infinity, I'm going to get this as 0. Okay, both of these fellows are going to get 0. At x equal to 0, you will have this as 1, this as 1. So basically, I'll write it here. So it is 1 upon 2, 1 upon iota 4 plus 4 minus of, okay, divided by, at infinity, this would be 0, and at 0, it would be 1 by. So I'll simply get 4 upon 2, and this is like iota 4 minus iota 4 minus 4 divided by iota 4 is, this is minus 16, and this is minus 16 again. So this iota 4 gets cancelled. Forget about it. Minus 4 is minus 8. Minus 8 into 4 is minus 32. Minus 32 you're getting down. So the expectation value of cos 4x, according to the probability distribution function f of x equal to e की power minus 4x, defined for all x greater than 0, turns out to be 1 by 2. Okay, I hope this is quite clear to you. Now let us take one more example, and the same thing you can do for the wave functions. The same thing one can do for the wave function. Let us take one example, and then we'll see all the questions in detail in the next session. All the more physics oriented questions we'll see in the next what you can say lecture. So let us take one more example. Okay, let us consider that a wave function of an electron in one dimension is given by. Now we want to find the expected position. We want to find the expected position. We want to find the expected position. So in order to find the expected position, what do we need to do? So in order to find, I'm writing it here, in order to find the expected position, what I need to do, I need to do from minus infinity to plus infinity. Now here, when I'm doing this, I know that the probability density is given by psi x mod whole square. Okay, and it is a real function. So basically it is equivalent to writing psi x whole square. Okay, so since the wave function is supplied to us, and we are not supplied with the probability density. So we know from our understanding of quantum mechanics that the probability density is given by psi mod whole square or simply psi x whole square in this particular scenario. Okay, so what I'll do, I'll simply write x into this particular thing square. So this is, I think, 12 e to the power minus 2x, and then I'll get 1 minus e to the power minus x whole square dx. Okay, so this is equals to, okay, oh, so sorry. This is the probability defined for all x greater than equal to 0. So I'll simply write not in. So it is like 0 to infinity. From 0 to infinity, 12 will come outside. And here I will have x into e to the power minus 2x. And then here I will have 1 plus e to the power minus 2x minus 2 e to the power minus x dx. So expectation value of x is simply 12 times integration from 0 to infinity x e to the power minus 2x dx plus x into e to the power minus 4x dx minus 2 x e to the power minus 3x dx. So this integration from 0 to infinity, this integration from 0 to infinity. Okay, now and all this multiplied by 12 also, sorry, all this multiplied by 12 also. So expectation value of x would be simply, or expected position for the electron would be 12 times. This is simply okay, so this is n factorial. So if I'm going to write the formula here, the formula is like this: integration minus st t raised to power n, if n is natural, then it is equals to n factorial divided by s raised to power n plus 1. So it is like 1 divided by s raised to power. So basically it is minus, it's not in minus, I think it is 2. So 2 raised to power, I hope it is clear. I'm using this formula, okay? So what I'll get, I'll simply get 12 times 1 by 4 plus 1 by 16 minus 2 by 9. But in this entire scenario, I have not checked that whether the wave function is normalized or not. So if it is not normalized, so let us normalize it. So I have to divide it by the integration. So in order to find the true expectation value, I need to divide it by integration from 0 to infinity. Sorry, integration from 0 to infinity psi mod whole square dx as well. Okay, I have to divide it by integration 0 to infinity psi mod whole square dx also. Okay, so this is one. Let us do that also. Let us see if it is normalized or not. So let us check it here. So I'll check it here. If it is normalized, then I don't have to divide it. If it is not normalized, then I will have to see. So 0 to infinity, what would be psi mod whole square? It would be simply e to the power minus 2x, 1 minus e to the power minus x whole square dx, and then 12 should also come outside. So it is equivalent to writing 0 to infinity. It is e to the power minus 2x minus 2 e to the power minus 3x plus e to the power minus 4x dx. Okay, so this is like this. Okay, so I'll get here, I think 1 upon 2. Okay, I think integration e to the power minus 2x is minus 1 upon 2. Because 0 to infinity is there, so 1 upon 2, and then minus 2 upon 3, and plus 1 upon 4 times 12 also. So what I'll get from here, it is like 6 minus 4. 888, sorry. So it is equals to 1. Okay, so that's absolutely fine. So I didn't, even if I forgot, there was no such worry. So expectation value of x, or expected value for the electron given by the wave function 2 root 3 e to the power minus x times 1 minus e to the power minus x is simply this. So 12 times this is, so I'll have to take a LCM here. So let me take LCM as 144. Okay, so if I take a LCM as 144 here, so what I'll get, I'll simply get 36 plus 9 minus 32 times 12. So what am I going to get? I'm going to get this expected value as simply 36 minus 36 plus 9 is 45 minus 32. It is 13 divided by 12. So expected value is 13 divided by 2. Okay, it's 13 divided by 2. What do you think the most probable position would be? So again, in order to find the most probable position, I told you the most probable position would be where your probability density has a peak. So most probable position would be simply xm given by that particular value where e to the power minus x 12 times e to the power minus x whole square, that is e to the power minus 2x. So it is e to the power minus 2x into 1 minus e to the power minus x whole square has a peak. Has a peak, or has a peak means it has to be maximum. So it implies that wherever you find the d by dx of e to the power minus 2x, 1 minus e to the power minus x whole square is the derivative is 0, there you'll have a peak, there you will have a maximum. So so it implies what? D by dx of this would be simply equals to d by dx of exponential minus 2x minus 2 e to the power minus 3x plus e to the power minus 4x, wherever it becomes 0, that particular point. So so it's quite easy to see that this would be minus 4 e to the power minus 4x plus 6 e to the power minus 3x minus 2 e to the power minus 2x equal to 0. And how to solve this? So let us take that e to the power minus 2x is simply, or I should take something common and then I'll do it. So what I'll do, I'll take something as common. So what should I do? Let me take e to the power minus 2x as common. So I'll get 4 e to the power minus 2x here plus 6 e to the power minus x here and minus 2. So if I take e to the power minus 2x common, then it is right. And I know that this is certainly non-zero. So it is always e to the power minus 2x is always non-zero. So whatever roots I'm going to expect, I'm going to find it from here only. So I can do one thing. I can write e to the power minus x as simply t. So I'll get minus 4t square plus 6t minus 2 equal to 0, or simply 2t square minus 3t plus 1 to be equal to 0 from here. And from here you can find this like 2t square minus 2t minus t plus 1 should be equal to 0. Fine. From here you are getting two values, t equals to 1 or t equals to half. So if t is equals to 1, so if t equals to 1, it implies e to the power minus x should be equal to 1, or e to the power minus x should be equals to 1 by 2. So let me see if I take the double derivative of the same. If I take the double derivative, so if I take the double derivatives, that is d2 upon dx square of f of x, leave the constant behind, just think about it. Just think about this. Just think about this. So what I get? I'll get 16 e to power minus 4x minus 18 e to power minus 3x plus 4 e to power minus 2x. And if I place x equal to 0, so if I place x equal to 0, I will simply get 16 plus 4 is 20 minus 18 is 2. It is positive. So x equal to 0, because e to power minus x equal to 1 means what? X equal to 0. So I can clearly expect that this cannot be the x equal to 0 cannot be the maximum quotient. Rather, it turns out that x equal to 0 is a local minimum. And one can easily find that this would be the value where you will have a local maximum. So this I'm leaving up to you. So x is equal to ln2 will be that value where where you can expect the x is equal to ln2 is the most probable position. Most probable position. It is the most probable position. So I'll write it as x. And if I want to find what would be the ratio of expectation value to the most probable position, it would be simply 13 upon 12 times 1 upon ln2. And I think it would be around, if I use the calculator, just give me a minute. So 13 divided by 12 will give me around 1.08. And I know this is 0.69. So it is around, I think, 1.563. Okay. These are some examples that I've given to you regarding expectation values, most probable values. I hope you will understand all these things if you go through this lecture. In the next lecture, we are going to make it a little bit more physics oriented, and we are going to discuss the expectation value of momentum operator, expectation value of position, like we did today for one of the questions, where we actually found the most expected position for a given wave function. Okay, so all these things I'm going to continue in the next lecture. Till then, take care. Bye.